Uh, I'll be talking about lattice-based locality-sensitive hashing. So this is a joint work with Karthik at UIUC, Daniel at CWI, and Ellen at Purdue. So nearest neighbor search problem is one of the most fundamental problems that has received a lot of attention because of many applications in like varied domains. So what this problem asks for is you're given a set of let's say n database points in d-dimensional Euclidean space, and the goal is to construct a data structure which, when given a query, quickly returns the closest database point to it. Okay. So this problem has been studied in a variety of metric spaces, but we'll be just focusing on the Euclidean space and L2 norm for this entire talk. So the problem with so for this problem, like it suffers from something which is known as the curse of dimensionality. That is, like if you try to build any data structure which performs better than the brute force linear search, then it would need preprocessing time, which is exponential, which requires either space or time exponential in that dimension. And in order to circumvent this problem, people have studied the approximate version of it, which is known as the C approximate R near neighbor search problem. So in this problem again, so you are given a set of n database points in d-dimensional space, and you want to again construct a data structure which does something as follows. So given a query point, if there exists a database point at a distance r from the query, then the data structure has to efficiently return a database point at a distance at most c times r from the query. Okay, and there are many approaches which have been used to solve this problem, and one of the main techniques that was used is known as the locality sensitive hashing. Okay, so in locality sensitive hashing, the goal is to construct a family of hash functions. That is, you want to hash each point multiple times uh, with the intent that the close points are mapped to the same bucket with higher probability than far points are mapped to the same bucket. Okay, so formalizing this notion, let's say P1 be the probability that two points which are close to each other hash to the same bucket. So by close, I mean something which is at a distance less than r. So we want them to hash to the same bucket with high probability. And P2 be the probability that these far points hash to the same bucket. And the goal for this LSH family is to construct hash functions such that there is maximum separation between this P1 and P2. And this separation is captured by a quantity which is known as the LSH constant. So this is the ratio between the logs of 1 over P1 and 1 over P2. And you can see, like for any non-trivial family of LSH functions, since P1, we want P1 to be much larger than P2, rho is always less than 1. Okay. And given this hash function, so given this family of hash function, like Indic and Motwani in their seminal paper had shown that suppose you're given a LSH function family with the parameters CR, P1, and P2, then you can construct a randomized CR approximate nearest neighbor search data structure, which answers query in time and space proportional to n to the rho. Okay, so basically, if you have any non-trivial family of hash functions, rho is less than 1, and you get a sublinear time and subquadratic space algorithm. Okay. Um, yeah, and the way you use the LSH family is you just hash the query again and just take all the points which are database points which are hashed to the same bucket. Okay. Yeah. So given this, like LSH has been very well studied, especially in Euclidean norms for L2 norms. So in the seminal work, so yeah, Indic and Motwani had given a construction of these hash function families over Boolean hypercube, which achieved an LSH constant of at most 1 over C. And this was later extended for Euclidean spaces. And Later, Alexandroni and Piotr Endick had given an LSH algorithm which uses ball partitioning scheme to partition the space, and their LSH scheme achieved a LSH constant of 1 over c square, and this was shown to be optimal. Okay. And in all these works, like these are in the classical setting, that is the hash function family is oblivious to the underlying database points. Okay, so it only depends on the ambient space and does not really depend on underlying database points. In a series of work later, like Alex et al. Had basically given an LSH scheme which depended on the underlying database points, and they circumvented this lower bound and they could achieve an LSH constant of about 1 over 2c square, which was again optimal. Okay. What we will be focusing on is just the classical LSH, the optimal LSH family. And so in their result, they had shown a couple of drawbacks. That is, the size of this hash function description that they have was very expensive. And it made it like prohibitive for practical applications. Also, the little o of 1, the convergence term to the optimal, it was kind of large, and people wanted to work with like reducing this little o of 1 term and improve on the rate of convergence to the optimal LSH. So we'll like briefly take a look at more details on how this scheme worked and the improvements that we suggested over it. So the optimal LSH family, like this is what they do. You first take the set of database points in d-dimensional space and project it to some lower dimensional space, let's say in Rk for some design parameter k to be chosen later. Now consider these grid of balls. That is, you take these integer points and put a ball of, let's say, radius w, where w is less than 1/4, about each of these integer points. And your goal is to like cover the entire space using random shifts of these grid of balls. As it turns out, like you would require large number of shifts of these grid of balls. So you would need about exponential shifts of these grid of balls to cover the entire space. And the hash of a point is just defined as the center of the ball in which the projected point lies. Okay, you can break ties in a certain order, but this is what the hash function does. And they have shown that this hash function achieves optimal LSH constant, where the convergence factor to optimal, the little o of 1 term goes to 0 as k increases. And the main drawback here was like to store the hash function description, like you needed to store all the k to the k shifts. So the hash function description was kind of expensive. And also the time to evaluate the hash of a particular point, you might have to iterate over all the k to the k shifts, which made this approach a little prohibitive for practical application. So to make it more practical, the authors themselves had suggested a different partitioning scheme of the space. Like instead of taking something like exponential shifts of a grid of balls, they suggested taking one shift of a random lattice. So lattices induce a natural space partitioning, and then they tried to use this to improve on the performance. So what are lattices? Like just briefly going over them. So lattices are just periodic arrangement of points in space, and they can be defined as the set of all integer linear combinations of some set of linearly independent basis vectors. So they look something like this. And these lattices, they induce a natural space partition with respect to the Voronoi cells. So what are Voronoi cells? So these are just, so Voronoi cell about any lattice point is just the set of all points in the ambient space which are closer to the lattice point than to any other lattice point. So in this specific example, the polytope here describes the set of points which are closer to 0 than any other lattice point. And if you take these Voronoi cells about each lattice point, you can tile the entire space. Okay, and this was what they used. So specifically, Andoni and Nindek had shown an alternate hash function. That is, you take the set of points, project it to a lower dimensional space, pick a lattice or one random shift of a lattice, and the hash of any point is now defined as the center of the Voronoi cell in which it lies. Okay. So they had given some experimental evidence using lower dimensional 24-dimensional Leech lattice to show that yes, they do indeed perform better. Uh, but they had left open the question whether lattice-induced space partitions can actually give us optimal LSH constant. And in this work, we resolve this problem saying yes, we do have actually lattices which achieve optimal LSH constant. Okay. So going into more details of the hash function, so this is how we define our hash function. So it is exactly similar, just that the choice of lattice changes. So you take these set of points in RD, project it to a lower dimensional space, and we project it using a projection matrix whose entries are pegged IID from a zero-centered Gaussian of variance 1 over k. So this is done just to approximately preserve the distances in the projected space. So, and now you pick a random lattice of determinant 1 from the Siegel measure. So this was an invariant measure which was like the existence of which was shown by Siegel in 48. And later Aitai had given a sampling algorithm to sample a lattice from this measure. Okay. So we pick a random lattice from Siegel measure. So it's a lattice of, it is a measure on lattices of determinant 1. So you pick one of these lattice and now just do a random shift of it. Okay. And again, similarly, like the hash of a point is now defined as the center of the Voronoi cell in which this projected point lies. And just from the properties of the Voronoi cell, this just happens to be the closest lattice vector to the shifted and projected point. Okay. So in order to hash a point, we now need to solve this closest vector problem on the underlying lattice, which in itself, like we know it is NP-hard in general, but there do exist single exponential algorithms which can achieve this in randomized space and time. Okay, so this is, so yeah, we do have a hash function which can hash a point in time about 2 to the k plus some little of k. So this is our hash function, and we show that there do exist lattices. So in particular, we show that in expectation, if we pick a lattice from the Siegel measure, it is expected to be good. So it achieves an LSH constant, which is optimal. And from probabilistic method, we do get that, okay, there does exist a lattice of determinant 1, which achieves the optimal LSH constant. One thing to note here is that this convergence factor, the little o of one term that we have, it's about 1 over root k, which improves on the previous approaches. Even though it's a slight improvement, people like practitioners are interested in reducing this, like improving this rate of convergence. Okay. So in order to show this proof, we'll have to like just go over, I'll just go over a very brief overview of this proof. So let us first define something, the collision probability. So let's say P delta is the probability that 2 points at a distance delta hash to the same bucket. Okay, so we first show that this quantity is well defined. So the P delta doesn't actually depend on A and B, but just depends on the distance between A and B. Okay, and in order to show that this, so in order to show that the lattice achieves an optimal LSH constant, we need to compute tight bounds on this P delta for delta being R, which is the near case, and delta being C times R, which is the far case. Okay, and the goal is to compute tight bounds on this P delta quantity. So just from the definition of our hash function, it turns out that this collision probability is exactly equal to the probability that a randomly chosen point in the Voronoi cell of a lattice remains in the Voronoi cell after a Gaussian perturbation of variance, let's say delta square over k. Okay, and this is the quantity that we wanted to understand. So it kind of turns out difficult to understand this probability with the Voronoi cell in picture. So the Voronoi cell is a polytope with exponential number of facets, and it's a kind of an ugly beast to work with. So we want to shift our view to something which we know better. So that is, we use the following observation that any point x is in the Voronoi cell about the origin, if and only if the open ball centered at x of radius norm x does not contain any lattice points. So this just follows from the definition of the Voronoi cell, that is 0 is the closest lattice point to it. Okay. And now this collision probability turns out to be exactly the probability that the union of these two balls, the following two balls, which is one ball which is centered at x of radius norm x, and one ball centered at x plus y of radius norm x plus y, does not contain any lattice point. Okay, so this is the quantity that we want to find tight bounds on. Um, Again, like estimating this quantity turns out to be difficult, but it turns out that these were the kind of quantities which were estimated in random lattice theory by Siegel and Rogers way back in 1958. Okay, so what we can instead do is estimate bounds on expected value of this collision probability. Okay, and yeah, so now the modified goal is to compute this tight bounds on this expected value of collision probability for delta being the near case and the far case. Okay. And we use these precise estimates which are obtained from random lattice theory, obtained by Schmidt and Rogers. So Schmidt actually gave a precise estimate on this exact value. Like he said that the expected collision probability would be something of that form, provided the volume of the two balls is tiny. Okay. If the volume is not too tiny, if it is large enough, then we had to use something else which was given by Rogers. And just combining these existing results, what we get is that this expected collision probability is equal to this expression. And you can note that this expression here is independent of the underlying lattice now. It only depends on the volume of the union of these two balls. And this volume can be tightly bounded by the sum of the volume of these two balls up to a factor of half, right? And then all it remains is to compute this integral. Uh, so computing this integral, like even though it's simple, it is just a double integral of two log concave functions. It turns out to be a pretty messy computation, and we need to be very precise. And after computing these integrals, what we get is that the expected collision probability is exactly of the form e to the minus alpha delta square, where alpha varies in a constant range for delta being in a range from k to the 1/4 to about square root k. So just using this estimate and plugging in delta to be r and c times r, we get that the expected collision probability in the far case is exponentially smaller than the expected collision probability in the near case. And now using Jensen's inequality, we get what we wanted to show. That is, there exists a lattice of determinant 1 which achieves the optimal LSH constant. Okay. So yeah. So in conclusion, we had shown that there do exist lattices which are LSH good, but the result is just an existential one. We can make it constructive by sampling a different lattice and checking for it, but it would be good to get a constructive solution. Moreover, what we are doing is sampling a random lattice for which all we know there is an exponential time algorithm to solve CVP. It would be good to understand if we can construct lattices with more structure for which we can achieve this optimal LSH constant, but they do have efficient CVP algorithms. And also one more drawback of this work that I wanted to point out was, like we had shown that for every dimension k and a given approximation factor, there exists a lattice. So for every approximation factor, we sample a different lattice. But it would be good to show if there exists one lattice which works for all approximation factors. And these are the two main open problems which I believe would be of interest to people. Okay, so thank you.
CDP, when you use the CDP there, you could have worked with an approximate CDP probably, sufficiently good approximation. Know that there is anything.
Possibly, but even for let's say polynomial approximation factor, CVP does not really do much better. Like yeah, like it has to be square root and kind of approximations.
Okay, thank you. Yeah.